All right, this video takes a look at Newton's method and another example of it that really shows some uniquenesses about Newton's method here. Uh, One of the nice things it shows is that you gotta be kind of careful how you do things, because if you're not, bad things happen. So in this example, we're taking a look at 3 times the square root of x minus 1 minus x. And so if we just write down what Newton's method is, if we want a better approximation, so this is x sub n plus 1 is equal to, we have to take the previous version and subtract off the x coordinates minus the function value at that value of x divided by the derivative at that value of x. Okay, this was simply just a matter of going through iterations and using the point slope form to kind of prove this, and I do have a video on that. In this one, however, we are going to push. We're going to push very hard against this this requirement of convergence. And so I thought it'd be kind of nice to show this particular example. So I've gone ahead and downloaded a TI-84 emulator. I'm going to turn it on here. I have already thrown the function in to my y equals function plots. Now, one of the things I want to mention about this TI, you'll notice it might look a little different than yours. For the TI-84, and I'm not sure about the 83, but back in January of 2011, TI released an upgrade to the operating system for the TI-84, and it changed some functionalities of it. It added some functions pertaining to mixed numbers, fractions, how the calculator reported them, that sort of thing. And it also went into kind of a pretty print function. It displays things better, although for diehards like me, it's a little tough to get used to. There are some additional improvements. I just haven't had a chance to explore all of them yet. However, that's for another day. So I've gone ahead and plotted this and graphed it here, but if we just kind of play around with this, I want to calculate a zero, which is what Newton's method does. And now I have to create a left bound. Say, so we'll take that and we'll create a right bound, and then we'll guess and we'll say, oh, okay, well, we have a zero at 1.145 or 1.146. 1.146. And then if I calculate the other zero, then I have to take a left bound and then a right bound. As soon as that y goes negative, we can click it. And then I get 7.854. 7.854. Well, now we're all kind of set up to go, except we need the derivative. And so let's go ahead and take the derivative of this function. This is going to be 3 times the derivative of the root of x minus 1, which is 1/2 the root of x minus 1 underneath, times the derivative of what's inside, which is simply 1. And so that particular term is all set to go, minus the derivative of x, which is 1. So now that we have our derivative, we can go ahead and go into Excel. Now this part I've already done. I've loaded in the original function, which is 3 times the square root of x, which is our value here. Okay, minus 1. After the root has been closed up, I also subtract x again. And for the derivative, I have 3 divided by 2 times the square root of that stuff. And after all of that is done, I subtract off 1. And then this is just a matter of the second, or the right half, if you will, or the right side of Newton's method. It's simply this piece. And now m plus 1, my next refers back to that. Okay, simply just to say, oh, that starts a new iteration. Now, if we look at what we've done here, we notice that in the domain of f, x cannot equal 1, or frankly, be less than 1, because that would give us a complex radical, or a complex root, and we don't like those, not yet anyway. So, same thing down here, we would have an issue with the derivative once we got into complex numbers if x is less than 1. And so x has to be greater than 1, because if it was 1, it'd be 0, and the derivative would not exist. And so But if we look, watch this. So I pick 1.1. Oh, and it settles down quite quickly to this value here that we've gotten. Okay. And so 146. And that settles down pretty quick. A couple iterations and bang, it's done. Excel can't tell the difference. Okay, well, let's try 1.2. Oh, okay, well, that settles down. 1.3. Oh, that settles down too. 1.5. 1.5. And now this just goes nuts. And it's just odd. So why does that happen? Because if we do 1.2, whoop. Let's go. Go back up here. 1.3. Take a look at this last number over here. Okay. Now it's getting closer and closer and closer. 1.4. It's getting closer and closer to 1. Now if we if we look at it, 1.45, all of a sudden it gets below 1. Okay, so now our value here gets below 1. If you look, we can't have that. This is essentially the very next iteration, and that's below 1. It turns into a complex number. We just can't have it. And so there's a limit there as far as how far away we can get from that 0 before we just kind of, the whole thing just kind of poops out, and we can't use it. And so this goes back to that idea of the sufficient condition, that if the absolute value of f of xn times f double prime of xn all over f prime of xn squared is less than 1, then it will converge. Well, it doesn't converge, and so we can declare that this must be greater than 1. And that's actually the contrapositive, not the converse. Please don't get the two screwed up. It diverges, and therefore we say this is bigger than 1. Not this is bigger than 1 and therefore diverges. That's not what I'm saying. So be logically correct. Now, this kind of fails. And so we can't pick certain values. But all of a sudden, if we go to, say, 3, oh, we can't pick 3 either. Well, maybe if we go to 6. Oh, whoa, 6 works. But wait a minute. It converges to a different number. Huh. So what this is really saying then is you need to be, when you're using Newton's method, you need to be close. Your guess has to be sufficiently close to the value of the 0. Otherwise, it doesn't work. Okay, so really, it's kind of a good idea to have an idea of where this thing is going to occur, because you never know how close you're going to have to be. Some of these functions you might have to get like within a frog's hair, which is really small if you haven't never seen a frog's hair. All right, so those things can happen. So just be careful of them, and I highly recommend graphing any of these when you're working with them.